In the last episode we learned how to use one of these two-way gamepads with a Genie in Circuit Wizard. So it's basically two potentiometers in an X and Y. So we're playing around with an analog input with that. Now I'm going to use exactly the same program on here. I've just pulled out this and I'm going to rearrange it a little bit and play around with some environmental sensors in this episode. So we're going to play around with an LDR, basically a light dependent resistor, and some thermistors here. Now this packet here, the little green blobs on the end of two wires, these tell me that they're 5k, so 5 kilo ohm resistors, variable resistors. And then this I don't actually know what resistance it is, so I'm going to do a quick little test. I think it's in the same ballpark, so let's start off with 20k on the multimeter. Touch these two together, I get a reading of 2.34 kilo ohms. So yeah, I was pretty right. Now if I hold my finger over it, you can see it goes up past 20 because it says open circuit there. So I go up to 200k, the next range 28, 29. Okay, so I was right, that's the kind of resistance I was imagining. Now we're going to connect these as potential dividers, a bit like with a potentiometer. You've got three pins. You've got a 0 volts, a plus volts, and then the wiper in the middle will range from 0 to the full voltage, whatever you're using. Now there's a little analogy to remember which way round these work. So I think of ice cream. It's a bit of a strange analogy, but both light and heat. Imagine a hot sunny day. It's bright and it's sunny. Your ice cream melts, so it flows, and that means there's not much resistance. That's the analogy I think of. So ice cream or chocolate or something like that melts, flows. So therefore, if it's bright, if the daylight's on, or the lights are on, sorry, you imagine the resistance to be low. Now if you remember with a low resistance, if we imagine, I've just rearranged this breadboard so that now we've got, we're still sharing the 3 pins here, so we're still sharing the 5 volts and the 0 volts with the LCD screen. So I'm going to connect 5 volts, and on this one here I'm going to start with a thermistor. I've just plugged it into this random old jumper cable, just so I can dunk it into a mug of tea. Okay, and I'm going to plug this up to the 5 volt rail, and then I'm going to use a resistor. Start off with a similar range to what we're expecting, so we're going from 2 to 20 something with the LDR. So I've chosen a 4K7 resistor, it's called, so that's 4,700 ohms. So that's going to go from the 0 volt rail, the ground, to the same column as this thermistor here. Okay, and then the analog input, which we'll use, let's use on the first one, we're going to just plug into there. Okay, so the midpoint of that is the voltage going into the analog input. Now I'm going to do the same for the light dependent resistor, but this time I'll put the resistor at the top and the LDR, there it is, in the same column. I should have put it down below, and that goes down to 0 volts. Now what does that mean? Well, this, if you imagine I put the resistor, sorry, the LDR at the top, when it's bright, not much resistance, so that allows more voltage to flow through that. So we get a higher voltage if the LDR is on the top and it's bright. If it's on the bottom, it's the other way around. So less resistance means more resistance here, so the voltage drops. Have a look at the video on potential dividers if it doesn't quite make sense. We'll go into it in a bit more detail. But yeah, you'll notice having that way, obviously I block it up. Well, let's have a look and see what happens. Right, so just get it in a slightly better view. Let's have a go and see if this works. Right, so we've got two readings here for the thermistor, and they're kind of as expected. They're somewhere in the middle of the range, so bearing in mind this is an 8-bit system, so the data range is from 0 to 255. So let's see. The LDR, obviously when I block it, higher resistance, so that means more, this is a lower relative resistance, so more voltage can go through there. And the value goes higher. Let's have a look. Room temperature, we've got the thermistor saying about 87. Put my finger on it, it goes up to 105, 106, 108, yep, seems to be working fine. Let's try a hot cup of tea. So just put this here, so we can see it. Now I want to be careful not to dip the wires into the tea really, because they'll make a well, they'll decrease the resistance between them, the hot liquid will. But you can see that goes right up to 172, 3. So yeah, we've got a decent thermometer. Now, obviously it's not much use as a thermometer with this data range. So in a minute I'll show you how to convert that to being a more useful value like a degree C. Instead of having the X value as the temperature, we can use a little conversion formula to work out an actual useful temperature like degree C. Now obviously I just dunked the thermistor in a cup of tea. I didn't know what temperature that cup of tea was at that point. I approximated the room temperature, so this is going to be very inaccurate. But the principle will work if you make much more accurate measurements and you use this formula, or rather this method of doing it. By the way, the algebraic type people might be able to work out a formula straight away. If you're visual like me, you probably just want to draw a graph and work it out this way. So what we've got here are the two readings we had. There's the room temperature and there's the cup of tea and the relevant X values that we read off the LCD screen. So what I've done here, plotted it on the graph, and you can see where the lines and the line converges. So where temperature should be 0, we would have an X value of about 38. So first thing, we're going to just subtract 38 from X just to shift that graph so that it's at 0, 0 there. And then if you had a direct conversion, it should be 45 degrees, so like 1 to 1, so they'd be the same values. So to get it 45 degrees, we've got to multiply this value up, or rather multiply this value down. Okay, so because we're changing this value. So what I've done here, you work out if you're going to kind of bring this value down, you're going to divide it, or rather scale it up by a number smaller than 1, so it's going to get smaller. So that is the way I've just worked out which ratio to go. Is it 14 divided by 6 or 6 divided by 14? They're just an approximate number of squares I counted up to work out that ratio. And it comes out at 0.429. So these two bits I'm going to put into Circuit Wizard.
Here we are with our gamepad controller program, which we've been using already for the sensor readings. Now, remember in the last episode I was talking about assigning the analog input 1 to being a variable X and then plotting that as the LCD value. We could have just gone straight in and plotted the analog input value there. But the point is, it's good practice just to assign it to being a variable, as I'll demonstrate now. So we're going to do some maths on that variable. Firstly, we are going to subtract 38. So we come down to expression. So remember, this is the one I'm always saying. It's got a lot of versatility to it. So I'm going to say C now. I'm going to have a new variable called C, and we're going to take X and subtract 38. First of all, I could label it, but I'm not going to. Now we could also use it to multiply by the scale factor, or rather divide. However, the trouble is you only have whole numbers with this method of doing it, whereas if you use the scale thing here, you can have fractions. So here we're going to scale C, and we are going to scale it by our calculated scale ratio, which is 0.429. Okay, and again, it is good practice to label it if you're doing your own work, but you're getting the gist just by what we're doing now. We're not going to come back to it. And instead of having the X value, I'm going to have this. So I'm going to put temperature equals variable C and then degree C. Now I think I'm probably going to get bogged down with it, but you can draw your own character as well if you wanted a degree, something like that. But trouble is we're going to kind of lose all the other information, I think, so we're not going to do that.
Right, let's see if it works. Now we plugged it in, it looks like it's got a very believable ambient temperature here. Back to how it should be, about 22 degrees C. So yeah, our scale, oh, it's dropped down to 21, that's fine. Scale looks okay. Let's see if it goes up to about 60. Bear in mind it's been a few minutes since I last measured it, so the tea might have cooled down a bit, but these mugs are pretty good holding the temperature. So let's see how hot it gets to. 56, 58. Remember, if I dip it in too much, like that, I'm actually going to conduct between the two wires, so it's going to be even less resistance, and obviously you'll read an even hotter temperature. The deeper I go, the hotter it'll say anyway. So obviously it's not a very accurate thermistor there with my mug of tea, but it gives you an idea of how you can use a scale factor in Circuit Wizard to be able to change an analog resistance, an analog input like that, and make something useful out of it. So another form of sensor, resistive sensor we can use is a force or pressure sensitive resistor. Now these come in different shapes and form factors and force amounts. This one here is a 20 kilogram one, and this one I've wired up to some jumper wires is a 5 kilogram one. I'm going to use this one, and we'll use it in the same form as the other two things I've just shown. So we'll use it in a potential divider, but the thing is this one has to be much higher resistance, so it is a much higher resistance to get the similar kind of thing. So now I've got it wired up to a Genie, but I've just thought I'd find out the voltage in the midpoint of this potential divider. So I've got a, it's only a 10k variable resistor here, or potentiometer, but I'm only using the 2 terminals here, so it is a variable resistor. And then the midpoint, so this is on the other side of the potential divider, and the midpoint I'm just measuring the voltage relative to 0 volts. And you can just tweak it so you can get the best reading. So being such a high resistance, it's going to be at the most part. So if I turn this up to one part here, I get the full voltage pretty much. And then I can just tweak it until obviously the other end is probably, well, it's about the ballpark of half the voltage. So it just means when I squeeze it here, I can drop it down to about 2 volts. So obviously this is a much bigger resistance than that. Now if we had a bigger variable resistor here, we might be able to get a better reading, but I'm going to obviously have it at about 10k to get that midpoint for the analog reading, to get a decent enough range. Right, here I've got the same thing, so we've still got a potential divider. This time I've just sent an output signal onto this LCD, so I've just got the analog reading here, and I've tuned it so I can get a nice looking analog amount from 0 to 255. I've turned it the other way around as well, just so that the heavier I push, the higher the number. Just makes life easier. And then here I've got a really simple set of scales. It's just basically a tube with a pencil, sawn off pencil on the end of it. So if I put a known weight like 100 grams on it, let's see what I can get. So about 16 on that. It's not very accurate obviously because I've got to hold on to it, which is going to take some of the weight anyway. So we'll say 100 grams is 16, sorry. Doing a mess of it there. 200 grams, let's just slide another weight onto there. See what we can get. Right, 25, 31. again, it just depends. Obviously you can see this is a very, very rubbish set of scales, but just proves the point, because obviously balancing it depends where the pencil might not be sitting dead straight on the sensor, all sorts of variables there, but I think I got about 21, yeah, so 21 on that, so 16, 21, 300 grams, 46. Now this will also point out how inaccurate the whole thing is, because when I plot a graph of this will be all over the place as well, but we might be able to correlate a fairly straight line and then get a conversion factor out of it. But the real problem here is my balancing it directly onto the pressure sensor, which is not really possible perfectly, and it's a very, obviously, very crude thing here because it's all over the place. But hopefully it will prove the point anyway. So 50, let's just say, and then one more, let's say 500 grams. 62, 64 maybe. Yeah, okay, 64. Okay, so I just plot a graph of that. They didn't actually come out too much of a discrepancy after all, actually. You can see it's a little bit wonky here and there, but I've drawn a straight line through here, and just for ease we'll say that value there is correct according to this line. Now you could certainly extrapolate a straight line with much more accuracy, but that one seems to be pretty good, and then it just makes the conversion factor easier. So at 500 grams we had 64 on the screen, so I can work out 500 by 64 is 7.8125. Now on Circuit Wizard, if I, rather than plot out the variable A0, sorry, the analog input, I'm going to assign that to variable A equals A0, and then I'll scale it by A times 7.8 to give me an approximate weight. Now that is what I've done here, and I've uploaded it, so now I've got, oh, and I've just stuck a G on the end so we know it's grams. And we can see how good it is. So I've got a motor here, unknown weight. I'll just stick that on there, see what I've got. 200 and... Remember, there's a lot of variables here, especially when I've got a trigger mechanism hanging off it as well. But let's try and get a kind of approximate, say 203, 211, 242. Let's see how heavy it really is. So we'll get a proper set of scales here. I'll just put that on like that. 250, 62 and 41, depends where I hold those cables. So yeah, you can see it's actually quite good, even though it's just one sensor like that. Now this set of scales will have 4 sensors on it, which will give an average reading. So it'll take an average of those 4 amounts and then plot it onto there. And it'll work in much the same way as this one.